All right, it's an exciting day. We've got claims about the mean. And since we've already done the setup about how hypothesis testing works, that means we can go ahead and just dive into the examples. So for the first example, students that succeed in pre-calculus. So how long has it been since their last math class? The idea being, if you take a long break in math, especially sequential courses like algebra, pre-calculus, calculus, that long break can mean that you're going to have a hard time getting back into it. So here we go. So by success, I'm talking about getting an A or a B. So for those that got an A or a B, I had asked them how many semesters since their last math class. And I'm going to test the claim that it is less than one semester. So maybe somebody took off no semesters, they went from algebra to pre-calculus. Maybe somebody took off one semester. When you average that out, let's say that it's going to be less than one. So I asked 40 pre-calculus students, and the average was the 0.725, and of course we need the standard deviation. Next, the claim. So since it's about the mean, that means we've got mu, in this case, less than 1. And when the claim has a less than, H1 can be the exact same thing. If the claim has any type of equals, H1 has to be the opposite. But with less than, it can stay less than. And then that tells us when we draw the picture, it's going to be a left-tailed test. H sub O ignores what everybody else does, says, you know what, I'm just going to put equals no matter what. And notice in here, in the directions, I didn't say what percent to use for the confidence level. So that means go ahead and use 95%. So whenever it's not mentioned, you automatically use 95%. So alpha will equal 0.05. Then draw a beautiful little bell-shaped curve like this. Since n equals 40, that means degrees of freedom is 39. And since it is left tail, the left shaded area will be a 0.05. And now I need to look up the critical value. What table should I use? Well, here it is. In chapter 8, 3 easy steps. If it's about proportion, you're going to use Z, that's table A2. If it's about the mean, then you use T, and that's table A3. And if it's about standard deviation, then use chi-squared, table A4. So chi-squared in table A4, that's going to be in the next section, 8.4. Something for you to look forward to. So bring out table A3, and this is 0.05 in one tail. So go up here to where it says one tail, and 0.05 means use this column over here. And then go to degrees of freedom of 39, and that is this little magic square right here. So degrees of freedom 39, go over to that column, 1.685. But of course, since it's on the left, it would be a negative number, so write it down as negative 1.685. And then let's use the calculator. So you would go to Stat, Tests, and this is the t-test. You see that one up there that says z-test? Ignore it. We don't use it anymore. Go to t-test. So when you go to t-test, then it's going to say, oops, sorry. So when you go to t-test, it's going to say right here, mu with the 0. So that's talking about when you look at H sub O, what does mu say? 1. So put a 1 right there. Then this is the X bar from the given information, the S, and it's based on 40 people. And then this little arrow right here should be pointing to the left, telling the calculator it's a left-tailed test. And then this black bar, under that it says calculate, so hit calculate. And it says that t is equal to a negative 2.429. So go ahead and write that down. And then you need to show where that lands on the picture. So a negative 2.429 would land over here to the left. So it does make it past the negative 1.6. Negative 2.4 is over here on the left. And then that means we actually did prove something. If it lands in this non-shaded area, that means we didn't prove anything. There's not enough evidence to prove anything at all one way or the other. But when it lands in the shaded area, that means yes, we did prove something. So the first thing to do is say reject H sub O. That's the official way to say yes, the test statistic landed past the critical value. Then look at the claim. Well, when this lands to the left side of the graph, that means that less than is true. If it lands to the right side, it means greater than is true. So in this case, is it less than 1? Sure enough, a 0.725 is less than 1. Now you might think, obviously 0.725 is less than 1. Why do we have to go through all that? But this is then saying for all of my pre-calculus students, this then applies. That the average for those that get an A or B, and we're talking about in the future, we're talking about my class this semester, by the end of the semester, those that get an A or B. So it's making a generalization, not just is this number smaller than 1. So the generalization is, at least for my students, in pre-calculus, if they get an A or B, the gap in their math is actually less than 1 semester. All right, how about example number 2? So movies that are rated PG-13 or R, so in other words, the movies that are meant for older people, do they last longer than movies that are for kids? Since kids have a shorter attention span, the movies for older people probably do last longer, but let's see. So for kids movies, the average 118.9 minutes. So a little bit less than 2 hours. Once you tack on the 45 minutes of commercials at the beginning though, okay, don't get me started. Anyway, so test the claim that for the PG-13 and R, it's going to be longer than that. So I looked at 19 big budget films from 2013. Wow, I really should update this example. Anyway, it's from 2013. They lasted an average of 141.3. Yep, that's longer. But there's a lot of variation, 28.9 minutes. That's nearly half an hour. As you go from movie to movie, that's a lot of variation. So the claim is coming from this right here, longer than, so bigger than. And since this claim does not have an equals, H1 does the same thing. So this arrow pointing to the right means it's a right-tailed test. And like I said, HO always just has equals. And like the last example, test the claim doesn't say what percent level of confidence to use, so use 95%. Or in other words, alpha equals 5%. Good job, alpha. Then be sure to write down the sample information, the N, X bar, and the S. And then next, the picture. So degrees of freedom equals 18. I was just noticing how sloppy that is. Sorry about that. Anyway, DF equals 18. Shade the right tail. And then look up the critical value. So here's the table. And it is one tail, 0.05. So we use this column. And then degrees of freedom is 18, so go down to right about here. 1.734 is the critical value. So put that on the picture, and Bob's your uncle. Okay, then should we do the formula ourselves or should we do the calculator? Okay, calculator. So once again, use the t-test. So here's the data. So this number right here where it says mu0, that comes from H sub 0, HO. So it's really just this number that's in the claim is what goes right here. And then this needs to be the X bar, the S, the sample size, and then this should point to the right. Then just choose calculate. And it says T equals a 3.379. So go ahead and write that down close to the graph. And then 3.3, so the question is, does this go past a 1.7? Yes, 3.3 is bigger than the 1.734. And since it landed in the shaded area, reject H sub O, which is just a fancy way to say, hey, we proved something. It doesn't tell us what was proved, but it just says, yes, you proved something. So what did we prove? The claim was that the movies for older people, it's going to be longer than for kids. And this, since it's landing to the right, means bigger than. So it's true. This sample over here of just 19 movies is then proving, yes, the movies for older people, they last longer than for younger people. Another example, you say? Okay, example number 3. So I did a pre-calculus, and now what about calculus class? So I claimed that they're going to have an average of 75 on exams by the end of the semester. 75 is a perfectly average. This semester, on the first exam, there's 47 students. That's a big class. And the average, 81.4. That's a very good score for the first test. And a standard deviation of 12.2. So the claim is that they will have an average, so that means that it's equal to. H1 cannot have equals, so it's going to be the opposite, not equals. And when it's not equals, that means two tails. Like always, H sub O has equals. And be sure to always write down the data. Here's the information that I use, N, X bar, and S. And then the picture. Sorry about that. I scanned that one 4 times. I told it to do it the highest resolution, and it's still blurry. Technology. Anyway, hopefully you can still see it. So it's a two-tailed test. So here's the two tails. And degrees of freedom is 46. So it's time to look at table A3 again. So this one's going to use a different column because now we're using this part that says two tails. Two tails with 0.05 means use this middle column and then go down to where degrees of freedom is 46. And you'll see over here, they don't have a 46. So whenever the table doesn't have what you need, use what's closest. So that would be using this 45. And then the little magic square says the critical value is 2.014. So then put negative 2.014 on the left, positive 2.014 on the right. And then for an extra treat, we're going to do the formula. So the formula is the same as the z-score. You take the x bar minus the mu divided by the standard deviation and then divided by the square root of 47. If you don't want to use the formula, then just use the t-test, but to change things up, I felt like using the formula. So anyway, pop that into a calculator, and it turns out to be 3.596. Of course, that 3.5 lands to the right, if I can get the magic arrow to work, yay! So, since the test statistic went past the critical value, once again, that means we proved something. The official way to say that, reject H sub O. So we're saying this equals 75 is not true, which is what the claim said. So that means the claim is false. But in this case, false is actually a good thing. Because this is landing to the right, it means that their average is actually going to be higher than 75. Now, since we're using 95% confidence, when I say this, that their average is actually higher than 75, I'm 95% confident that's true. There could be some strange thing that happens, but for the most part, I can be pretty confident that their mean is going to actually be above 75. Good job for them. All right, so I'll see you next time when we test the claim about standard deviation.